Okay friends, welcome back. Today again we are going to discuss about rise time, delay and bandwidth. So what is delay of systems in cascade? So what is the delay of systems in cascade? One delay measure is the time it takes for the impulse response to reach its center of mass, that is the normalized value of its first moment. So h of t, td and t. So the bandwidth region is delta t. So td is equal to minus infinity to infinity th th of t into dt minus infinity to infinity h of t into dt. So impulse response, the block diagram, the figure is like this. So Td is equal to minus infinity to infinity th of t dt by minus infinity to infinity h of t dt. This is also known as Elmore delay. Delay time can also represented in terms of Fourier transform of h of t. So h of f is equal to minus infinity to infinity h of t into e power minus j to phi of t dt is approximately equal to h of 0 is equal to minus infinity to infinity h of t into dt. So d by df of h of f that tends to f is equal to 0 is equal to minus j 2 pi t minus infinity to infinity h of t into e power minus j to pi of t into dt, that is minus 1 by j2 pi d by df of h of f that tends to h f is equal to 0 minus infinity to infinity th of t into dt. So again Td is equal to minus infinity to infinity th of t dt by minus infinity to infinity h of t into dt. Specifically the first moment is minus infinity to infinity th of t dt is equal to minus 1 by j2 phi into d by df of h of f. F is equal to 0. The normalization factor is simply the dc gain. Minus infinity to infinity into h of t dt is equal to h of z 0. Delay of systems in cascade, so that t of d is equal to minus infinity to infinity th of t into dt by minus infinity to infinity h of t into dt is equal to minus 1 by j2 phi h of 0 df d by df of h of f is equal to 0. Using this definition, the delay for a single pole low pass system is just the pole time constant tau. Consider two systems with impulse responses h1 of t and h2 of t with corresponding Fourier transforms h1 of n and h2 of f. We know that the Fourier transform of these two systems in cascade is just the product of the individual transforms, so that h dot is equal to h1 into h2. And next, therefore, the overall time delay is t of d comma total is equal to minus 1 by j2 pi h1 of 0 into h2 of 0 d by df of h1 into h2 f is equal to 0, which we may expand to obtain t of d comma tot is equal to minus 1 by j2 pi h1 of 0 into h2 of 0 h2 of 0 into dh1 by df f is equal to 0 plus h1 of 0 into dht by df of f is equal to 0. Td comma total is equal to td1 plus td2. The overall delay of a cascade of systems is simply the sum of individual delays. The time required for a pulse to rise from 10% to 90% of its steady state value. The second moment useful in defining the rise time, The quantity delta t is a measure of the duration of the impulse response and hence also a measure of the rise time of the step response. Specifically, delta t is twice the radius of gyration about the center of mass t of d of h of t. From first year calculus, we find that delta t by 2 whole square is equal to minus infinity to infinity t square h of t into dt by minus infinity to infinity h of t into dt minus td whole square. Again, we can use our Fourier transform identities in practical. Minus infinity to infinity t square h of t dt is equal to minus 1 by 2 pi whole square d square by df square h of f is equal to 0, so that t square rise is equal to delta t whole square, that is equal to 4 into 1 4 into minus of 1 by 2 pi square d square by df square h of f by h of 0 minus of 1 by j2 pi h of 0 d by df of h of f is equal to 0 whole square. The rise time is given by the rise time is given by t square rise is equal to 4 by 2 pi square h of 0 h of 0 h of 0 minus d square by df square h of f is equal to 0 minus 1 by h of 0 d by df of f is equal to 0 whole square. The Elmore rise time for a single pole low pass system is 2 tau. Now consider two systems each with its own rise time. Then t square rise comma total is equal to 4 by 2 pi square into h1 of 0 into h2 of 0 of minus d square by df square h1 into h2 f is equal to 0 minus 1 by h1 of 0 into h2 of 0 d by df of h1 into h2 f is equal to 0 whole square. After simplification, this leads to the desired result that t square rise comma total is equal to t square rise 1 plus t square rise 2. The square of the overall rise time is equal to the sum of the squares of individual rise times. T rise comma total is equal to square root of t square rise 1 plus t square rise 2. So the bandwidth rise time relations. The simple relation for bandwidth and rise time is omega minus 3 dB T rise is approximately equal to 2.2, where W minus 3 dB is the minus 3 dB bandwidth in radians per second, and and T rise is the is the 10 to 90% rise time in response to a setup. Consider the simple RC low pass filter shown in figure. Consider 10%, consider 90%. TR is equal to T2 minus T1. 0.1 is equal to 1 minus exponential form of minus T1 by RC. Exponential of minus T1 by RC is equal to 1 minus 0.1. Exponent minus T1 by RC is equal to 0.9. T1 is equal to minus RC integral of 0.9. Consider 90%, 0.9 is equal to 9 minus exponential of minus T2 by RC. Exponential of minus T2 by RC is equal to 1 minus 0.9. Exponential form of minus T2 by RC is equal to 0.91. T2 is equal to minus RC integral of 0.1. TR is equal to T2 plus 1. TR is equal to RC integral of 0.9 plus RC minus RC integral of 0.1. TR is equal to RC integral of 0.9 by 0.1. TR by RC is equal to 2.2. TR is equal to RC into 2.2. The simple relation for bandwidth and rise time is omega minus 3 dB. T rise is approximately equal to 2.2, where omega minus 3 dB is the minus 3 dB bandwidth in radians per second, where T rise is the 10 to 90% rise time in response to a setup. Consider the simple RC low pass filter 0 to 1. The value is about 10% higher than the Elmore rise time. The step response of a two-pole system d naught of t is equal to 1 minus 1 by 1 minus z square e power minus I omega nt sine of 4 whole power square 1 minus omega nt plus 5, where uh, phi is equal to 10 tan inverse of the equation, and the 3 dB bandwidth of the system is given by WH. For the extreme case of a damping ratio of 0, the rise time and bandwidth are given as this. Okay, given as this following.